grounding electrode conductor is a dedicated conductor specifically designed to carry fault currents and provide a low impedance path to ground. This helps ensure electrical faults are cleared quickly and safely, reducing the risk of electrical shock or fire. A grounding electrode conductor is a permanent conductor not subject to the same wear and tear as a grounded conductor. This makes it more reliable and less likely to fail, which is critical for ensuring the safety of the electrical system. The National Electrical Code requires the use of a grounding electrode conductor in most cases where a grounded conductor is used as a grounding electrode conductor. This is because the National Electrical Code recognizes that a grounding electrode conductor is the best way to ensure the safety and reliability of the electrical system. While it is possible to use a grounded conductor in place of a grounding electrode conductor in some cases, it is important to understand the risks involved and to take steps to mitigate those risks. For example, if a grounded conductor is used as a grounding electrode conductor, ensure it is properly sized and installed, and that it is not subject to damage or corrosion. The considerations are safety, reliability, and National Electrical Code compliance. On a typical residential installation, it is best to use a grounding electrode conductor for this duty. This will help ensure the safety, reliability, and code compliance of the electrical system. Here's a breakdown of why a dedicated grounding electrode conductor is generally preferred. Firstly, safety. A grounding electrode conductor provides a direct, low impedance path for fault currents to return to the source. This helps to quickly trip over current protection devices like circuit breakers, minimizing the duration of a fault and reducing the risk of electrical shock or fire. Grounded conductors, on the other hand, are primarily intended to carry normal load current. While they can also carry fault current, they may not always provide the lowest impedance path, potentially delaying the tripping of protective devices. Secondly, reliability. Grounding electrode conductors are typically sized and installed to withstand the stresses of fault currents. They are also less likely to be inadvertently disconnected or damaged compared to grounded conductors that might be used for other purposes. This dedicated and robust connection ensures a consistent and reliable grounding path. Thirdly, code compliance. The National Electrical Code, or NEC, has specific requirements for grounding electrode conductors to ensure effective grounding. Using a dedicated grounding electrode conductor simplifies compliance with these requirements and provides a clear and verifiable grounding path for inspectors. Now consider the risks of using a grounded conductor as a grounding electrode conductor. 1. Shear path. When a grounded conductor is used as both a neutral conductor and a grounding electrode conductor, fault current can flow through it along with normal load current. This can lead to voltage drop on the grounded conductor, potentially affecting the performance of sensitive electronic equipment. 2. Impedance. The impedance of a grounded conductor may be higher than that of a dedicated grounding electrode conductor, especially if the grounded conductor is undersized or poorly connected. This higher impedance can impede the flow of fault current, delaying the tripping of protective devices and increasing the risk of electrical hazards. 3. Corrosion. Grounded conductors can be susceptible to corrosion, especially in damp or corrosive environments. Corrosion can increase the impedance of the grounded conductor, reducing its effectiveness as a grounding path. Now let's discuss grounding electrode conductor sizing. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. National Electrical Code Table 250.66 provides guidance on selecting the appropriate size of grounding electrode conductor based on the size of the service entrance conductors. For example, if the service entrance conductors are 2/0 American wire gauge copper, the grounding electrode conductor must be at least 6 American wire gauge copper. The grounding electrode conductor must be connected to a grounding electrode. Common grounding electrodes include ground rods, ground plates, and metal underground water pipes. The grounding electrode must be installed in accordance with National Electrical Code requirements. For example, ground rods must be driven at least 8 feet into the ground. Now, let's discuss the exception mentioned in National Electrical Code section 250.142. The exception number 2. This exception allows the grounded conductor to be used as the grounding electrode conductor for certain ranges, dryers, counter-mounted cooking units, and wall-mounted ovens under specific conditions. The grounded conductor must be part of a cable assembly or raceway. The equipment must be supplied by a single-phase 120 or 208 or 120 over 240 volt circuit. The grounded conductor must be no smaller than 10 American wire gauge copper or 8 American wire gauge aluminum. The grounded conductor must be insulated. This exception is based on the understanding that these appliances are typically located near the service entrance and that the grounded conductor provides a low impedance path to ground. However, it is important to note that this exception is not universally accepted, and some jurisdictions may not allow it. Also note the risks associated with using the grounded conductor as the grounding electrode conductor. One is shared neutral current. As mentioned earlier, when a grounded conductor is used as both a neutral conductor and a grounding electrode conductor, fault current can flow through it along with normal load current. This can lead to voltage drop on the grounded conductor, potentially affecting the performance of sensitive electronic equipment. 2 is potential for shock. If the grounded conductor becomes disconnected, the appliance can become energized, creating a shock hazard. 3 is reliance on insulation. The exception requires the grounded conductor to be insulated. However, insulation can degrade over time, potentially compromising the safety of the installation. While the National Electrical Code permits the use of grounded conductors as grounding electrode conductors in certain situations, it is crucial to carefully consider the potential risks and benefits before making a decision. When in doubt, consulting with a qualified electrical inspector can help ensure that the installation meets all applicable safety requirements. Now let's consider the grounding electrode conductor material. Grounding electrode conductors can be made of copper, aluminum, or copper-clad steel. Copper is the most common material used for grounding electrode conductors due to its excellent conductivity and corrosion resistance. Aluminum is less expensive than copper, but it is also less conductive and more susceptible to corrosion. Copper-clad steel is a good compromise between cost and performance. The grounding electrode conductor must be protected from physical damage. If the grounding electrode conductor is exposed to physical damage, it must be protected by conduit, armor, or other suitable means. The grounding electrode conductor must be continuous. The grounding electrode conductor must be continuous from the service equipment to the grounding electrode. Splices are not permitted in grounding electrode conductors. Now let's discuss grounding electrode connections. The grounding electrode conductor must be connected to the grounding electrode in a manner that ensures a permanent and effective ground. Connections must be made using listed connectors or clamps. Connections to ground rods must be made using exothermic welding or listed connectors. Connections to metal underground water pipes must be made within 5 feet of the point where the water pipe enters the building. The grounding electrode system should be tested periodically to ensure that it is functioning properly. Testing can be performed using a ground resistance tester. A ground resistance tester measures the resistance of the grounding electrode system to earth. The resistance should be as low as possible, but it should not exceed 25 ohms. If the resistance is greater than 25 ohms, the grounding electrode system should be improved. The methods of improving the grounding electrode system include driving additional ground rods, replacing the existing grounding electrode with a larger one, and treating the soil around the grounding electrode with a ground-enhancing compound. Now, let's talk about the importance of proper grounding. Proper grounding is essential for electrical safety. A properly grounded electrical system helps to protect people from electrical shock and fire. It also helps to protect electronic equipment from damage. A grounding electrode conductor provides a low impedance path for fault currents to return to the source. This helps to quickly trip over current protection devices like circuit breakers, minimizing the duration of a fault and reducing the risk of electrical shock or fire. Proper grounding also helps to reduce voltage fluctuations. Voltage fluctuations can damage sensitive electronic equipment. A properly grounded electrical system helps to stabilize the voltage, protecting electronic equipment from damage. Proper grounding can also reduce electrical noise. Electrical noise can interfere with the operation of electronic equipment. A properly grounded electrical system helps to reduce electrical noise, improving the performance of electronic equipment. When designing and installing a grounding system, it is important to follow all applicable codes and standards. The National Electrical Code provides detailed requirements for grounding electrical systems. It is also important to consult with a qualified electrical inspector to ensure that the grounding system is properly installed. So, to summarize the key points, firstly, a dedicated grounding electrode conductor is generally preferred for safety, reliability, and code compliance reasons. Secondly, using a grounded conductor as a grounding electrode conductor can introduce risks related to shared neutral current, impedance, and potential shock hazards. Thirdly, when using a grounded conductor as a grounding electrode conductor, ensure compliance with National Electrical Code Section 250.142, the exception number 2, and carefully consider the potential risks. Fourthly, proper grounding is essential for electrical safety and protecting equipment from damage. Lastly, always follow applicable codes and standards and consult with a qualified electrical inspector when designing and installing a grounding system. Now, let's discuss the types of grounding electrodes. 1. Metal underground water pipe. A metal underground water pipe is the most common type of grounding electrode. The water pipe must be in direct contact with the earth for at least 10 feet. The connection to the water pipe must be made within 5 feet of the point where the water pipe enters the building. 2. Ground rod. A ground rod is a metal rod that is driven into the ground. Ground rods must be at least 8 feet long. They must be driven into the ground at least 8 feet apart. 3. Ground plate. A ground plate is a metal plate that is buried in the ground. Ground plates must have a surface area of at least 2 square feet. They must be buried at least 30 inches below the surface of the earth. 4. Concrete encased electrode. A concrete encased electrode is a metal conductor that is encased in concrete. The concrete must be in direct contact with the earth. The concrete encased electrode must be at least 20 feet long. 5. Ground ring. A ground ring is a metal conductor that encircles a building or structure. The ground ring must be buried at least 30 inches below the surface of the earth. It must be at least 20 feet long. Now let's delve into the requirements for grounding electrode conductor installation. 1. Protection from damage. The grounding electrode conductor must be protected from physical damage. If the grounding electrode conductor is exposed to physical damage, it must be protected by conduit, armor, or other suitable means. 2. Continuity. The grounding electrode conductor must be continuous from the service equipment to the grounding electrode. Splices are not permitted in grounding electrode conductors. 3. Connection methods. The grounding electrode conductor must be connected to the grounding electrode in a manner that ensures a permanent and effective ground. Connections must be made using listed connectors or clamps. Connections to ground rods must be made using exothermic welding or listed connectors. Connections to metal underground water pipes must be made within 5 feet of the point where the water pipe enters the building. Now consider additional grounding and bonding requirements. 1. Equipment grounding. Equipment grounding conductors are used to ground non-current carrying metal parts of electrical equipment. Equipment grounding conductors provide a low impedance path for fault currents to return to the source. This helps to quickly trip over current protection devices like circuit breakers, minimizing the duration of a fault and reducing the risk of electrical shock or fire. 2. Bonding. Bonding is the process of connecting metal parts of a building or structure together to create an electrically continuous path. Bonding helps to reduce voltage differences between metal parts, minimizing the risk of electrical shock. 3. Surge protection. Surge protection devices are used to protect electrical equipment from voltage surges. Voltage surges can damage sensitive electronic equipment. Surge protection devices divert voltage surges to ground, protecting electrical equipment from damage. The grounding system plays a crucial role in the overall electrical safety of a building or structure. A properly designed and installed grounding system helps to protect people from electrical shock and fire. It also helps to protect electronic equipment from damage. Always ensure to consult with a qualified electrician when designing and installing a grounding system to ensure compliance with all applicable codes and standards. Consider the local amendments and interpretations of the National Electrical Code, as these can vary by jurisdiction. Local authorities having jurisdiction may have specific requirements or interpretations that differ from the national code. Also, periodic inspection and maintenance is crucial. Regularly inspect the grounding system for any signs of damage or corrosion. Ensure that all connections are tight and secure. Test the grounding system periodically to verify its effectiveness. The frequency of testing will depend on the environment and the type of electrical system. And remember to document everything. Maintain accurate records of the grounding system design, installation, and testing. This documentation will be helpful for future inspections and maintenance. Finally, consider special grounding requirements for sensitive equipment. Some types of sensitive electronic equipment, such as computers and medical equipment, may require special grounding arrangements to minimize electrical noise and ensure proper operation.